Okay, let's talk about alcohols. This is Dr. B, and they have the general formula of not CnH2n plus 2, but CnH2n plus 1 with the OH. Now, really, it's the same as CnH2n plus 2 when you account for the fact that there's a hydrogen right there. But think of oxygen as not changing the overall ratio for an alcohol. It's almost like a spacer, if you will. It got in between the carbon and the hydrogen. Fine. So that's the general formula if they are saturated. And since they have an electronegative oxygen, that's a nucleophile right there, and that can attack things. They can be secondary, primary, tertiary, right? This one would be primary, monosubstituted. This is disubstituted, secondary, trisubstituted, tertiary. Can't be quaternary because you've run out of bonds. One of them we humans have a special enzyme for, and that's ethanol, which is perhaps one of the most abused drugs on the planet. All right, let's go over the typical chemical reactions that they undergo. Yes, they are flammable, so they burn. So if you hit the right temperature and you have oxygen present, it's a high temperature, you can turn them into carbon dioxide and water. We can, in addition to this combustion reaction, get them to oxidize to aldehydes if they are at the end, if they're primary, or ketones if they are secondary. And this is a minor oxidation. We're not going all the way up to the carboxylic acid. And what's happening is since this is getting oxidized, something must be getting reduced. And that would be this chromium here can get reduced. It must be in a relatively high oxidation state. So it gets reduced. It gains those electrons. And you can do the opposite. So like we said, if it's a secondary alcohol, you can make a ketone. If it's a tertiary alcohol, well, then it can't do anything, right? Primary makes aldehydes, secondary makes ketones, and tertiary, well, you've run out of bonds and they won't react. Now, you can go the opposite way. If you have an aldehyde or a ketone, you can reduce it down, and this time we need a reducing agent. That's typically hydride, right? So this H here, or H minus, they'll attack that carbonyl, and you'll get an alcohol. Another thing that we can do is bring them all the way up to the carboxylic acid. We can call this major oxidation or reduction. It's the major one is, once again, that means this is an oxidizing agent. It itself will be reduced, and it can render that alcohol go right past the aldehyde or ketone all the way up to the carboxylic acid. And a strong reducing agent is lithium aluminum hydride. 4 H minuses per molecule, and these H minuses can attack the carboxylic acid and bring it all the way down to the alcohol. So this adds quite a bit to your arsenal in terms of oxidation and reduction. You can either go strong or weak. Another thing that we can do is turn them into esters. Carboxylic acids react with alcohols and they form esters. This would be a Fischer esterification in this process. Just loses water. Not the greatest way, but you can use these to make these esters. So there's the 2 carbons here that forms the alcohol part of the ester, right? And the carboxylic acid from which it was derived. In this case, it would have been acetic acid. This would have made ethyl acetate. This is how we make those alcohols. Briefly, you can imagine that there's your nucleophile. The carbonyl carbon, if you draw it out, is your electrophile. It attacks the carbonyl carbon, kicks out water, and you get an ester. What else can we do? Well, we can just eliminate them down to alkenes. So if we protonate this thing and lose water and another hydrogen from here, you can bring it down to the alkene. And if we want to substitute, we can. X minus can, under the right conditions, substitute, kick out the OH minus, maybe make it a better leaving group by having it protonate first, so you're losing water. And we can make alkyl halides that way. So this is several reactions that we can do with alcohols.